The P21331 MSD project involves the design of a high-speed data acquisition system, better known as a DAC, for rocket engine testing. Our DAC is capable of measuring acceleration and vibration using IEPEs, applied forces using load cells, temperature using thermocouples, and additional sensor types using a robust current loop protocol. My name is Joseph Eden, and I am a fourth-year electrical engineer.
Hi, my name is Ben Hebert. I'm a fifth-year mechanical engineering student at RIT.
My name is Anthony Bacchetta. I am a fifth-year computer engineering major.
Hello, my name is Jared Banju, and I am a fourth-year electrical engineer.
Hello, my name is Jay Mantini. I'm a fifth-year computer engineering student here at RIT.
This project is sponsored by Relativity Space. The team has created two of our DACs, with one being given to Relativity and the other being given to RIT Launch Initiative, RIT's rocket team. Here is the system-level block diagram for our DAC. The discrete modules shown in this figure will be described during this video. One of the primary sensors on our DAC is an acceleration sensor. IEPE stands for Integrated Electronics Piezoelectric. These sensors are used to measure acceleration, force, or pressure. In our case, we're using it to measure acceleration and vibration. An IEPE is typically implemented as a transistor circuit where a signal from an oscillating piezoelectric material is converted into a low impedance signal via the transistor. This circuit is energized with a constant current. Here is our design for the IEPE circuit front end. We're using a constant current IC to drive our IEPE, and the voltage output of the circuit is bandpass filtered and attenuated to meet the input range of our analog to digital converter. We are using a common ADC for the IEPE and all of the following circuits to reduce BOM count and allow for common firmware. The next sensor in our DAC is a full bridge load cell. Load cells are sensors that deflect when a force is applied. This deflection influences a change in resistance, and this change in resistance produces a proportional output voltage. Our load cell front end is implemented with constant current excitation. One inherent attribute to load cells is a very small output voltage. Therefore, we need to amplify our output signal significantly to make use of the full range of our ADC. Our full bridge front end has two stages of amplification. The first stage is an instrumentation amplifier, which is almost purpose-built for this application with a very high gain, and our second stage is a standard amplifier, providing the last little bit of gain to get us to our full ADC input range.
Another group of sensors on our DAC are K-type thermocouples. These sensors are used to measure temperatures between -200 and 1260 degrees Celsius. A thermocouple consists of two different metals welded together forming an electrical junction, known as the hot junction. When the two dissimilar metals touch, a temperature-dependent voltage appears due to the difference between the electric potential between the two metals. This is known as the thermoelectric effect. It is important to note the voltage measured across the two metals is representative of the difference between the ambient temperature and the temperature being measured. This means the ambient temperature needs to be measured to calculate the actual temperature under consideration. This maximum integrated circuit has an internal ambient temperature sensor and converts both temperatures to a digital form to be read by the DAC's microcontroller.
Another sensor apparatus on the board is the 420 mA current loop. Current exits the DAC from the current source, goes through an external 420 mA sensor, and returns to the DAC through a sense resistor. This sensor will limit the current allowed to flow to between 4 and 20 mA, proportional to the percentage of the measured process variable, such as pressure or temperature. At 4 mA, 0% of the process variable is being measured, while at 20 mA, 100% of the process variable is being measured. In order to determine the current, the sense resistor's resistance and the voltage across it are used in conjunction with Ohm's law. In order to measure the voltage across the sense resistor, we use an ADC. Since we dictate the resistance of the sense resistor with our part selection, and we know the voltage across it, we are able to use V equals IR to determine the current, and convert that to our process variable. In our implementation of this circuit, the current source will prevent damage from overcurrent if the user accidentally shorts it, as the current source will not allow for currents greater than our set threshold. Current sources are useful sensor architectures as the current flowing is used to power the sensor, so additional power supplies are not necessary at the sensor's location. There is also decent noise immunity as the current loop is low impedance.
The brains of the data acquisition system is contained within the firmware coded onto an XMC 4700 Relax kit. This firmware has the microcontroller communicate with the various sensors on the board by using a protocol called Serial Peripheral Interface, or SPI. Through the use of SPI, the microcontroller is able to send and receive data from the various peripherals of the device. By making use of SPI's chip select feature, we're able to specifically select which device we wish to receive data from at a given time. This is helpful for reducing the complexity of connections between the microcontroller and the peripherals. For instance, with thermocouples, even though there are 4 different devices we are currently reading data from, we're able to share the lines for data in, data out, and the clock signal to the devices. By setting one of the 4 chip select lines low, the microcontroller is able to specify which device of the thermocouples is able to make use of those lines to send the data back to the microcontroller. The firmware operates by sending periodic interrupts so as to read data from the peripherals to achieve the required sampling rate of the devices. All of the data received from the peripherals is stored along with the timestamp of when the data was recorded. This is all packaged up into an array in the microcontroller's memory for transfer to a computer over Ethernet.
Now that data has been processed by the microcontroller, it needs to be sent to a computer so that it can be analyzed. This is accomplished using an Ethernet cable. The microcontroller packages the data that needs to be sent to the computer. It then connects to the computer by sending a communication request. Once the computer sends back an acknowledgement, data begins to flow from the microcontroller to the computer. A program on the computer side then sends the data to a file that will be used when we analyze the data.
To provide power to all subsystems on the DAC, a series of voltage regulators were implemented with the maximum possible current draw in mind. Starting with a 28-volt power supply as an aerospace industry standard, the voltages are brought down to 26.15 volts for the IEPE, full bridge, and current loop interfaces, plus and minus 3.3 volts for the full bridge amplifiers, plus and minus 2.5 volts for the analog to digital converter, and 3.3 volts for the microcontroller and thermocouple interfaces.
Our circuit board is a 6-layer circuit board. The IEPE sensors are connected with SMA connectors on the bottom left, while the current loop and full bridge use standard DB9 connectors on the top left. The thermocouples use specialized connectors shown in the top center. Power enters the board from the connectors on the top right.
An important part of any electronic device is its enclosure. The enclosure allows for convenient storage and transportation, as well as protecting the electronic components from the elements. In our case, this enclosure was 3D printed to allow for flexibility and ease of redesign if necessary. Heat-set threaded inserts were used wherever fasteners were necessary due to their ease of installation and use, as well as plastic's poor performance with threaded fasteners. Our system is intended to be mounted vertically to the outside of a concrete test site during use, and that can be done easily using 1/4 inch bolts, which will pass through the flanges on the top and bottom of the enclosure.